Here we're going to analyze a common type of op-amp circuit called an inverting amplifier. And you can see in our circuit, here's the op-amp circuit symbol that we discussed. And in this circuit, you can see there's two resistors. This top resistor is labeled RF, F standing for feedback. Feedback is anytime you have a connection between the output and one of your inputs. So you can see here we have a resistor between V out and the inverting input. The non-inverting input is grounded, and then we have another resistor here, Vn, that's attached to not only the feedback resistor but also the inverting input. These are the rail voltages, or power supply voltages, plus V and minus V. Now sometimes in circuit diagrams the plus V and minus V are not explicitly shown, but if they're not shown, they're understood to be there because the op-amp would not do anything if it wasn't powered. Okay, because remember, this symbol represents that practical circuit of about a dozen transistors. So if you don't have these supply voltages, those transistors can't operate. Now over to the lower right here, this is the model, the circuit that we used last video to come up with the ideal characteristics of an amplifier. And what I've done here is I've replaced the input resistance with its ideal value of an open, and also the output resistance with its ideal value of a short. And this is going to help us do the analysis of this circuit, okay, because this part of the model represents the input side of the op-amp, and this part of the model represents the output side. So what we're going to do here is we're going to come up with an expression for V out in terms of V in. Okay, often this relationship is shown as a ratio. Okay, so you see this is what we want to find, and this is called the closed loop gain. A closed loop. Okay, closed loop gain. Alright, and the way we're going to do this is basically a node voltage expression here at this node that I'm going to label A. Okay, so this node right here, we're going to call node A. And we're going to start off with the KCL equation. So, okay, KCL at A, and you can see I have I1 defined going in and IF defined going in. So we have I1 plus IF, and then that equals this current here, I, which is right at the input of the op-amp. Now, this is one of the reasons why I drew this model circuit. See, this current here right at the input of the op-amp, ideally that current's going to be 0 because the input resistance of an op-amp ideally is 0. In actuality, this Ri is not infinity, but it's a really high resistance, like several million ohms. So in reality, this current's very small, and in most cases, that negligible current doesn't have much an effect on the result of our closed loop gain. So the ideal analysis that we do in this class is very close to what you would actually see if you hook this circuit up in a lab situation, as many of you will taking the lab portion of this course. So you see here little I is equal to 0, and this is because Ri is ideally infinity. Okay, so now we have that I1 plus IF equals 0, and we can continue with our node voltage method where we write I1 and IF in terms of voltage using Ohm's law. So this is this is the method you learned in your circuit theory class. So I1 would just be V in, voltage on the plus side, minus VA, okay, the voltage on the lower end side of R1, and then divided by R1 to get current. And then I'm going to take IF to the over to the other side of the equal sign, so now it's minus, okay, minus IF. And then IF is going to be V0 minus VA So we're getting close to what we want, V out over V in. Now we can do another simplification, because if we look at VA and then also consider what VI is equal to. VI, that's the voltage between the two inputs of the op amp. So again, in the model, it's this voltage right here. Now we can come up with the ideal value of VI by looking at the output side of this model. If the output resistance is the ideal value of 0 ohms, a short, then V out is just equal to AVI. Okay, so now if I just write this in terms of VI, right, VI is equal to V0 over the open loop gain A, remember that constant, and remember the ideal value of open loop gain is infinity. So what you get is that ideally the voltage across the input of a op amp is 0 volts, right? Any finite number divided by infinity is 0. So not only is the current 0 at the input of an ideal op amp, but also the voltage across the inputs of an ideal op amp is 0. Okay, so since the non-inverting input is grounded, and since this voltage across the inputs is 0, that means the voltage on the inverting input is also 0, and that's where VA is. Okay, so you see VA here can be simplified to 0, and that's because VI is 0 along with the non-inverting input being grounded. Okay, so now if you just rearrange for V out over V in, you see that the closed loop gain for an inverting amplifier is just minus the RF resistor divided by R1. See, this is our closed loop expression for the inverting amplifier. Now you can see that it comes out that this closed loop gain is just reliant on the value of the two resistors, and there's also this minus sign, and this minus sign indicates inversion. Okay, so the minus indicates that inversion has taken place. Okay, and inversion just means that V out is 180 degrees out of phase with V in. Okay, and we'll do a couple examples to illustrate exactly what that means, but for now just know that the minus sign, that's indicates inversion is taking place between the output and the input. Now the last thing that I want to mention here is just a term, and we'll squeeze it over here. Okay, we saw earlier in our models that both the current at the input of an ideal op amp and that's a 0, and the voltage across the inputs of an ideal op amp are both 0. Okay, again, this I, this V, both 0. Well, this is called a virtual short. Okay, so you need to know this term. Okay, so this is different than a physical short like you learned in circuit theory. A physical short, the resistance is equal to 0, and remember the voltage current relationship for a physical short, resistance equal to 0, is that there's 0 volts across a short no matter what the current is, right? The current could be anything, and there's 0 volts across a resistance of 0 ohms. Okay, this isn't the same thing. Virtual short, this term applies only to op amps, and in fact only to ideal op amps. And it's talking about that the current and voltage at the input of an ideal op amp are both 0. Okay, so don't confuse virtual short with, you know, shorts that you've known up to this point. Okay. All right, so that's our analysis of our first op amp circuit. We're going to be doing more of this in future videos. There's a handful or so of common op amp circuits that we'll be looking at.